So in this example, or this section, I should say, we're going to talk about what are called conditional probabilities. Conditional probabilities are where a probability is calculated after you know something has happened. So in other words, you're finding the probability of an event A given that something else has happened, maybe B. And this is known as conditional probability. So I know B's happened. I want to find the probability of A happening. So let's do some examples of this, of what this means. So let's say we roll 2 fair dice. So let's talk about what the sample space would look like here. The sample space would equal listing all of the different sides of your dice. And I'm gonna, it's nice when you can copy and paste. So I'm gonna do some copy and pasting here. Make this a little bit faster. And then I just need to change these to 2s. And then I'll change them to 3s. There's probably a quick way to do this even. Well, there was. I could have just copied a sample space when I already wrote it down somewhere. So I wouldn't have to do this again, but I didn't. But I'm almost done. I'm going to just move this one just a whoops. All right, one more. All right, so those are all of those. So now I can find the probability of a sum of 7, let's say. So the probability of a sum of 7 would be the probability going, you can actually go up the diagonal here. This diagonal 6, 1, 5, 2, 4, 3, 3, 4, 5, 2, 5, and 1, 6 are all the different ways of getting a sum of 7. So I'd have 6, 1, 5, 2, 4, 3, 3, 4, 5, 2, and 1, 6. Notice I'm putting these in a notation that is what we call probability notation. They set the event spaces in curly brackets, braces if you prefer, and then the probability is inside parentheses. All right. And counting wise is 1, 2, 3, 4, 5, 6. So there's 6 out of 36. And again, I don't reduce that normally. Let's do the probability of a sum of 12. Again, can up here, sum of 12 would be this one right here. So the only way to get that would be the probability of getting a 6, 6. Again, counting, there's only 1 there out of the 36. So there's your probability. So you can see it's way more likely you're going to get a sum of 7 than you are for a sum of 12. And then the same thing with the 8. find 8 over here. So 6, 2 is a way to do 8. Then 5, 3, 4, 4, 3, 5, and 2, 6. Oops. I listed this one not in the right order. It's 5, 3. All right. And again, I can count 1, 2, 3, 4, 5. It says 5 ways that can happen out of 36. Now, none of these were conditional probabilities. These were just finding the probability. We didn't know anything before we did them. So we just found the probability of sum of 12. We just found the probability of sum of 8. We went back to our original sample space. Now I want to find the probability of sum of 7, given that the first die is a 4. So if I look back at the sample space, I know I've been given the information that the first die was a 4. So I don't need any of the other values. I don't need this first row because I know the first die is a 4. I don't need this one. I don't need this one. I don't need the 5s, and I don't need the 6s. So the only things I need are the 4, 1 through 4, 6. So we can actually say we have a new sample space here, and we can actually call it, I like to call it a restricted sample space. And the restricted sample space is always the information that comes after the given. I've been told, this is my information I was told, I've been told the first die is a 4. So I have this new sample space. If you want to call it R, you can. For restricted, you don't have to. And that is going to be all the ways of getting a sum of 4 at the first die. So 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. And this is now my new sample space. I don't need to look at this other one over here because this big one here contained all of the other pieces. I can just look at this new one. And so now out of this new restricted sample space, what's the probability of a sum of 7 given a first die is a 4? Well, there's only one way out of this whole thing of getting a sum of 7, the 4, 3. So there's one way out of these 6 ways of this happening. So it's 1 out of 6. Let's do the same thing for the sum of 12, given the first die is a 4. So since I'm given the same information, I don't need to go and create a new restricted sample space. I can still use this sample space. Out of this sample space, how many ways can I get a sum of 12? Well, none. So this would be 0 out of 6, or 0. If I want to do the probability of the sum of 8, given the first die is a 4, again, coming back up here, how do I get a sum of 8? Well, there's one way, the 4, 1, out of this restricted sample space. So this is going to equal 1 out of 6. Let's do another experiment. Let's pull a card from a fair deck with no jokers. So again, we're going to first start off with what is our sample space. Our sample space would be all the cards. So the 2 of clubs, the 3 of clubs, the 4 of clubs, the 5 of clubs, the 6 of clubs, 7 of clubs, 8 of clubs, 9 of clubs, 10 of clubs, Jack of clubs, Queen of clubs, King of clubs, and Ace of clubs. And then I'd have the 2 of diamonds. And I'm not going to list them all. I can see I'm going to have that same pattern through the Ace of diamonds, the 2 of hearts, through the Ace of hearts, and the 2 of spades, through the Ace of spades. So there's my sample space. And then I can find the probability of an ace. So the probability of an ace would be the probability of getting any one of the aces. So my event space would be Ace of spades, ace of clubs, ace of diamonds, and ace of hearts. So again, there's 4 out of 52. So you just count. So as always, you're just going to count how many there were. 1, 2, 3, 4 out of 52 cards. Now I'd like to find the probability of an ace given that the card is black. Well, now I've been told some information. I've been told the card is black. So I don't need these hearts. I don't need these diamonds. I just need the clubs and the spades. So again, this given information is my new restricted sample space. I don't need the rest of the sample space. And it's just going to be the 2 of clubs through the ace of clubs and the 2 of spades through the ace of spades. So there's my restricted sample space. And so now out of this restricted sample space, what are the ways of getting an ace? Well, there's an ace of clubs and an ace of spades. There are only black cards, and there happens to be 26 black cards. So this would equal 2 out of 26. Again, I normally don't reduce this. Let's say I want to do a club given the card is a 10. So again, that given information is my restricted sample space. So I don't need all of the other cards. I don't need these 2s through 9s or the jack, queen, king, or ace. I just need those 10s. So my restricted sample space would be the 10 of clubs, the 10 of diamonds, the 10 of spades, and the 10 of hearts. So that's my restricted sample space. And now out of this restricted sample space, there's 1 club out of these 4 cards. So it's 1 out of 4. And those are conditional probabilities. Now, I want to point out something about these. One of the things I want to point out about these is that in some cases, the probability didn't change at all. In other words, looking at this, the probability of a sum of 7, given the first die was a 4, was equal to 1 out of 6. And the probability of a sum of 7 is 6 out of 36, which, by the way, now I will actually reduce, that is 1/6. So notice, knowing that the first card was a 4 didn't actually give me any information. Knowing that, not the first card, the first die, knowing that first die was a 4 didn't actually give me any information. The probabilities didn't change in any fashion because these probabilities are exactly the same. So these equal each other, and that didn't give me any information. But notice the probability of a sum of 12 given the first die is a 4. That was 0 out of 6. And remember, the probability of the sum of 12 was actually equal to 1 out of 36. And those don't equal. So knowing that the first die was a 4, did in fact change my probability. That actually affected what my probability was going to be. Knowing that this actually happened, that I got a die of 4, changed the probability of getting a sum of 12. Let's look at another one, the probability of a sum of 8 given the first die is a 4. That was 1 out of 6. But the probability of sum of 8 was 5 out of 36. So again, those didn't equal. So knowing that first die was a 4 changed the probability of it being a sum of 8. The probability changed given that information. Another one that we could look at is, back to our dice, our other one here, is we had 4 out of 52. If we knew that we had an ace, what's the probability of an ace given the card was black? That was 2 out of 26. Well, those both reduce to 1 out of 13. So those actually are equal. So knowing the card was black didn't change my probability in any fashion. That given information didn't help me at all. But if knowing the card was a club, given the card is a 10, that was 1/4. The probability of a club is 13 out of 52, which is also 1/4. So again, knowing that information didn't help me in any fashion. This gives us an idea of what we call independent events. Two events, we'll call them A and B, are independent if the probability of A, given that B's happen, equals the probability of A. In other words, knowing that A happens, knowing that B happens doesn't change the probability of A in any fashion. So in other words, what you can also say is that A and B are independent if knowing that one event happens does not change the probability of the other event happening. So as long as that probability doesn't change, then everything's fine. Okay. The way I think about this, if I ask people what's the probability that my 93-year-old father has Wi-Fi in his house, and most people would say, well, 93, chances are probably like maybe 10%. But then if I tell you that my dad has an iPad, then that probability goes up. So having an iPad changed the probability of him having Wi-Fi. And so that actually does affect it. So they're not independent events because the probability changed. If the probability didn't change, then they would be independent events. So knowing that your first child's a girl does not in fact affect the probability of your second child being a girl. Some people like to think it does, but it doesn't. And that means that they're independent events because the probability did not change. This gets us to the last rule. I don't really use this rule very often either, but it does say the probability of A and B. And it's called the multiplication rule for probability. And it says the probability of A and B is the probability of A times the probability of B given that A's happened. I don't like to use this one very often. Usually when I have and statements, I usually, again, like to just write out the event space and count. I find them much easier than trying to use these formulas, but they are useful for a couple places I'm going to show you. The other one I want to mention is if A and B are independent, and this is why we spent time on independence, then the probability of A and B is equal to the probability of A times the probability of B, because the probability of B wouldn't have changed given that A's happened because they're independent. So this one's useful also. Again, I don't use them very often. There's only a couple places where I use them. This is one of those places when, let's say my experiment is pulling 2 cards from a deck. When I pull 2 cards from the deck, my sample space would have to be listing every single card for the first card and then every single card for the second card. So that'd be 52 times 52. That's huge. That's 52 squared. That's a huge sample space, and I would not want to list that one out. So if your sample spaces are so large, like pulling multiple cards or other things like this, then these formulas are useful. And so what I want to do is I want to find the probability, I forgot to mention that, find the probability of getting 2 10s. Okay. So that's the first probability. And the first time we're going to do it, we're going to do it without replacement. What that means is I'm not going to put that card back. That card's going to stay out. So I'm looking for the probability of 2 10s, which that means I'm going to get the probability of getting a 10 on the first and a 10 on the second. So the probability of getting a 10 on the first card is there's 4 cards that are 10s out of 52 cards in the deck. So it's 4 out of 52. Now, if I'm going to do the probability of a 10 on the second card, I'm going to assume, the only way to get 2 10s is if I assume that second card, that first card was a 10. Otherwise, I can't get 2 10s. And the other thing I'm going to assume is I didn't put the card back. So that means that that first card was a 10. So there now are less cards in the deck. So the multiplication rule says, especially because I have a word and here, multiplication rule tells me this is the probability of 10 on the first times the probability of 10 on the second. But the probability of 10 on the first was 4 to 52. The probability of 10 on the second is not 4 to 52 because there's one card missing. In fact, oh wait, I'm sorry, this is with replacement. So we'll do without replacement first. So that card is missing. So without replacement, I did not put that card back. So since I didn't put that card back, that card's missing. I'm assuming the first one was a 10. So I'm assuming that card that's left out is a 10. So there's only 3 10s left. There's only 51 cards left in the deck. So this would be 4 to 52 times 3 out of 51. If we did it with replacement, then with replacement would be the probability of 2 10s would be the probability of a 10 on the first and a 10 on the second. Well, again, the first card is a 4 out of 52. There's 4 cards in the deck that are 52. Now this time I'm going to replace it. So I'm putting that card back. So if I'm putting that card back, then we have also still have 4 cards in the deck and we still have 52 cards in the deck. So we still have 4 10s and still have 52 cards. So you just multiply 4 to 52 times 4 to 52. And this pattern would keep going no matter how many you pick. So without replacement, that card is now missing because you didn't put it back. With replacement, that card is back in there. So the probabilities didn't change. So this one with replacement is independent, whereas without replacement are dependent.